In mission-critical systems, unpredictability is unacceptable. A single latency spike in memory retrieval can crash a high-frequency trading engine or stall an operating system kernel. We are diving into the structural bedrock that prevents this chaos: balanced binary search trees.
Consider a standard binary search tree. If you insert data that is already sorted, like the numbers 1 through 5, the tree skews entirely to the right. It becomes nothing more than a linked list. What should be a lightning-fast logarithmic search collapses into a slow, linear crawl. For millions of records, microseconds turn into milliseconds.
To solve this degeneration, computer science offers two primary contracts. The AVL tree is a strict disciplinarian, enforcing perfect height at all costs to guarantee the fastest possible reads. The red-black tree is the pragmatic alternative, trading a slightly taller structure for a guaranteed bounded cost during memory updates.
The AVL tree mandates that the absolute height difference between any left and right subtree never exceeds 1. Mathematically, it sits extremely close to the theoretical minimum height. But this rigidity has a price. Deleting a single node can trigger a cascade of structural rotations that ripple all the way up to the root, making it highly inefficient for write-heavy environments. Red-black trees relax the strict height rule, substituting it with a color-coded memory mechanism. By enforcing rules like preventing consecutive red nodes and ensuring every path down to a leaf has an identical black node count, the tree guarantees its longest path is never more than twice its shortest. This restricts the maximum height to 2 times log base 2 of n.
When an insertion violates the color rules, the red-black tree heals itself locally. First, it attempts a simple recoloring, flipping bits to push the violation upwards. If that fails, it executes a rotation, which is a constant time pointer swap. The genius here is the mathematical bound. An insertion requires at most 2 rotations, keeping cache invalidation to an absolute minimum.
In high-performance systems like the Linux kernel, every byte matters. Instead of creating separate objects for nodes, Linux embeds the tree node directly inside the data payload. Furthermore, because memory pointers are aligned, the bottom bits are always 0. Linux aggressively hijacks this empty space to store the red or black color bit, squashing the entire node down to just 24 bytes.
Compare that kernel-level efficiency with application layer languages. In Java, a tree map node carries the massive baggage of object headers, memory references, and padding, swelling to over 64 bytes per node. Switching to a standard hash map does not fully solve this, as hash map entries also suffer from object overhead. This heavy pointer fragmentation is exactly why developers handling massive datasets often abandon node-based objects entirely, falling back to primitive specialized collections or array-backed structures to survive.
Yet, the physical architecture of memory is changing. Modern processors move data in 64-byte cache lines. The pointer-chasing nature of red-black trees often triggers devastating cache misses, costing hundreds of CPU cycles per leap. This hardware reality is why modern languages like Rust are shifting away from binary trees entirely, adopting cache-friendly B trees for maximum performance.